Alright guys, so last time we were talking about this idea of change of state, which again might seem simple at first, but when we start talking about things like heating and cooling processes starts getting a little confusing. And also with energy. You haven't learned too much about energy yet, but it's a way of measuring the amount of energy or heat and how it moves. And from your reference table, let's just take a minute to review what we did last time. With evaporation, of course, we're going from liquid to gas. You've known that for years. It would take 2,260 joules of energy per gram of liquid water to convert it to a gas. And we call evaporation in weather a cooling process because it cools down the surroundings. And we use the example of taking a shower or going swimming. And when you get out of the water, you feel cold, even if it's a really hot day. That feeling might not last long. Once the water evaporates off your body, then you warm up really quickly. And that's what we mean by evaporation being a cooling process. It's cooling down the surrounding environment. In order to go from a liquid to a gas, we have to absorb heat. And we absorb the heat from the surrounding environment. In the case of taking a shower, well, it's the heat from your body that's causing the water on your body to be converted to a gas. And you're losing heat and feeling cooler. And that's why we like to go swimming and hang out by the water when it's hot. Condensation is the opposite in every way. The amount of energy is still 2,260 joules per gram, but now it's moving the opposite direction. So now instead of the energy going from the surroundings into the water, now the water the water vapor is releasing energy to the environment as it goes back to being liquid water again. And we call it a warming process. We're adding heat to the environment. We talked about melting, going from solid to liquid. Okay, this is a cooling process. We're adding heat to the solid. Think of an ice cube. You have to add heat to cause the ice cube to melt and convert it into liquid water. And if you have an ice cube in your hand, well, it's a cooling process because the heat from the ice cube, or the heat from your hand, is going into the ice cube, cooling your hand down. You feel cool, not because the ice cube is putting like coldness into you or anything like that. In fact, there's no such thing really as cold technically. Cold is just the absence of heat. So as the heat from your hand goes into the ice, we feel cooler. And that's what we mean by melting being a cooling process. And then again, we have freezing, the opposite. 334 joules per gram, just like melting. It's in your reference table. We're going from liquid to solid. So we're taking liquid water and we're freezing it. This is considered to be a warming process because we're adding heat to the environment. When we freeze water, we're pulling heat out of the liquid water and we convert it into ice, but that heat has to go somewhere, and it goes into the environment. And last time we took a look at the orange growers and how in Florida and in the South, they take oranges and they spray water on them, and that water freezes, releases heat to the environment, and keeps those oranges from freezing solid, saving the crop. Now there's two other phase changes that we didn't talk about before. We have sublimation and deposition. Sublimation is when we have such rapid heating that we go from a solid directly to a gas. And the best example that I can think of is dry ice. And you've probably seen dry ice like on Halloween and stuff like that. It's solid carbon dioxide. It can only exist at a very cold temperature. And when we have it at room temperature, it gets so hot that it skips the liquid phase, goes straight to gas. We can figure out how much energy that takes. And if we go to the reference table, we can see the 334 and the 2,260 from before. We would basically just add those numbers together. And we would have the total amount of energy. We're skipping melting, but if we did melting, that would be 334 joules per gram of energy, plus what it would have taken if it were a liquid, to go from liquid to gas, that's 2,260. So we would add those two numbers together, and that would equal the total. And deposition is the opposite. Now we're going from a gas directly to a solid. And a good example of this would be frost. We have water vapor in the air, and it gets very cold overnight, and it goes to solid ice crystals. We see those on the grass and on windshields of cars and so on, frost. And it's the same amount of energy, only now we're going the opposite direction. So it's going to be 334 joules per gram plus the 2,260 joules per gram. But the direction is going the other way. Instead of going from a solid to a gas, now we're going from a gas to a solid. So let's just summarize this all on this chart. So this chart is basically showing it with arrows. So we have ice going to water. That would, of course, be melting. Taking 334 joules per gram. We could go from liquid to gas. That would be evaporation or vaporization. It works the same whether we're boiling the water or letting it slowly evaporate. Just one happens faster than the other, but the concept is the same. And that's going to be 2,260 joules per gram. Now, if we take the gas and cool it down, we have condensation. (2,260 joules per gram of energy being released to the environment. So again, this is a warming process. This would be cooling. We talked about getting out of the water, you feel cool. Melting is a cooling process. We're taking heat from the environment, making the ice cooler. Think about holding an ice cube in your hand. It's going to make your hand feel cool. If we continue down this line, we go from liquid water to solid. Of course, that would be freezing. Freezing is technically a warming process. And I know that sounds very strange. But in order to freeze water, we have to pull heat out. We have to pull the heat out, and we warm the surrounding area. That's what we mean by a freezing process, or warming process. 334 joules per gram. And then we talked about sublimation. And we talked about deposition. And how we skip those phases, or we skip the liquid phase altogether, and we could add up the energy. Okay, so sorry about that. We add the energy together. Same thing here. Joule per gram plus 2,260 joules per gram. So we add those together during sublimation and deposition. And we can see here, one absorbs heat, one releases heat. The one with the dots absorbs heat, the one releases heat. If it's absorbing heat, it's a cooling process. It's cooling the environment. And if it releases heat, it is a warming process. And let's just do the next page of this, and then we'll stop for now. So moisture in the atmosphere. We have an abundance of water in the atmosphere. And almost all of the water in the atmosphere really comes from the ocean. The ocean makes up the majority of the world's surface. Other sources of water would be, of course, rivers, streams, lakes, so on. Well, when we're talking about water in the environment, we have all three states or phases. As a gas, we would call it water vapor. As condensation, or liquid, we have the tiny droplets suspended in the air. This is our condensation. And we even have tiny little crystals of ice suspended in the air that form clouds. And a lot of people don't realize many clouds are actually made up of little ice crystals, and we have solid. So even within the atmosphere, we have water in the form of a gas, we have water in the form of a liquid, and we have water in the form of a solid. We have water vapor, the tiny little droplets in, I'll say, low clouds, low altitude clouds. When clouds get higher in altitude, then we're talking about ice crystals suspended in the air, even in the summertime. Thunderstorm clouds are often made up of ice crystals, even in the summer. Remember, high in the troposphere, temperatures are low, low enough to have ice in the summertime. All right, so that concludes this video. That's all for now, and good luck.